Hi everyone, and thanks for attending this talk. I am Pedro Becker, and I'll be presenting the work Demystifying Power and Performance Bottlenecks in Autonomous Driving Systems. José María Arnau and Antonio González are the other authors of this work. All authors are with Universitat Politécnica de Catalunya. So this is the outline for our presentation, where I'll start presenting the motivation for our work together with our proposal in the introduction. Then I'll briefly present a background on autonomous vehicles that will be useful for understanding our methodology and our obtained results that comes next. Finally, I will discuss our conclusions. So let's start with the introduction. So in the very first place, I believe it's worth to question why investigate autonomous vehicles at all. In fact, there are many benefits in adopting autonomous vehicles for our society, as I'll try to highlight some of them here. So first, because it's a possible path for a safer traffic. In a recent report by the World Health Organization, they say that traffic accidents caused more than 1 million deaths and left between 20 to 50 million people injured worldwide during a single year. Also, according to Waymo, more than 90% of the traffic accidents in the US has some type of human participation. Also, we can argue that autonomous vehicles will lead to a better traffic, and this is because they are never distracted as humans, they rigorously obey the traffic legislation, and they do not decide to make a turn in the very last second just because they almost forgot the route. They always know the route in advance. And finally, we can also say that autonomous vehicles will create a more inclusive traffic, as they can be used as a personal end-to-end vehicle by elderly people, disabled people, and children, for example. However, fully autonomous vehicles are still under test and research because they must overcome a series of challenges. The computational system contains multiple software tasks to solve the different problems faced during the driving. Notwithstanding, these software tasks generally have to cooperate in a coordinated manner to actually achieve the goals. For example, autonomous vehicles must localize themselves and also identify other objects such as cars and pedestrians, classifying and localizing them in the scene. Then they have to track these objects and stipulate the routes, and only after that, the autonomous vehicle can choose a safe lane to drive by. Despite the software complexity, we also want autonomous vehicles to be fast. We can put a minimal requirement that they should react to the environment at least as fast as a human, for example, although we generally want them to be even better. This is necessary to guarantee a safe drive, processing the necessary actions to avoid accidents, such as braking to stop the vehicle and avoiding a collision. Note that this requirement holds for the whole drive time span. That is, the system may never miss a deadline, because otherwise the safety guarantees are lost and an accident is much more likely to happen. To define a roadmap in order to tackle down such challenges would be valuable if we could answer the following questions. First, how is the computation time divided among the computation tasks? Second, where are the bottlenecks of autonomous vehicles? And third, are we using the most appropriate underlying hardware to do that? If we can answer this, we can improve autonomous vehicle solutions to overcome the challenges that I just mentioned before. Before we present how we aim to answer these questions, let me briefly present a background on autonomous vehicle systems. We can conceptually divide autonomous vehicles into three parts. The first part is composed of a set of sensor devices such as cameras, LiDAR, inertial measurement units, and GPS that are used to capture signals from the environment around the vehicle. The vehicle should also have access to a high-definition map of the region it is about to drive. The data collected by these sensors are then continuously provided as input to the computation layer, where a set of pieces of software, also called nodes in the robotic jargon, are combined to solve a variety of goals. For example, finding the precise localization, performing object detection and object tracking, planning the route in advance, and navigation decisions are all solved in this layer. Also, note that although we have computation in nodes individually, we generally need to combine one or more of these nodes into a computation path in order to deliver the desired results. For example, we can only track an object if it was previously detected by the software node responsible for detection. Finally, we can update the vehicle state by interfacing the software decisions with the car, providing commands for steering, accelerating, or braking. Now that we have a background, we can take a look on the methodology that we adopted in order to try to answer the questions that I presented before. So the methodology starts by preparing the inputs, that is, map and sensor data that we use to stimulate software stack for autonomous driving. The software stack that we use, which performs the driving computations, is called Autoware. Autoware is a complete software stack for autonomous driving, and it is qualified to be used by autonomous vehicles in public roads in Japan since 2017. Also, Autoware is open source, which not only facilitates the characterization by us, but also the reproduction of our work and our findings by peers. At this point, it is also worth mentioning that the sensor data utilized to stimulate Autoware comes from a real-life set of sensors that were installed in a car and recorded during a driving. Hence, we can always provide real-life input to the software stack utilizing this data. Also, the tests were performed with an Intel i7 and an NVIDIA GTX 1080. We submit the setup to a series of profiling tools such as Vogrind, PAPI, NVIDIA SMI, ATOP, and also perform instrumentation in the code using, for example, the C++ Chrono library. In our methodology, we focus on the following measurements. First, we characterize the latency required by the software to perform the different tasks. This occurs both in the single node level as well as in the computation path level. That is, when we measure the time since a frame from a sensor enters the software stack until its final contribution to the driving task. We also assess the hardware usage and the power dissipated by Autoware. Finally, we collect microarchitecture metrics for key nodes in order to understand possible bottlenecks. The idea here is that knowing these microarchitecture metrics, we can also point out solutions for these bottlenecks. Finally, we acknowledge that we limit our analysis to the perception tasks of Autoware, since they contain the majority of the nodes and consume most of the computation time. If interested, you can also find more details of our methodology in the manuscript. Now let's take a look on the characterization results. Let's start the analysis of our characterization by understanding how we report the latency. The x-axis contains the different nodes that compose the Autoware software stack, while the y-axis presents the latency times of these nodes in milliseconds. Since nodes process many inputs while driving, we have a collection of latency values measured for each of these nodes, and naturally these nodes also have varying times of execution. For this reason, we depict the measure in these volume plots, which helps to understand how the measured values are distributed along the whole software execution. For each latency measurement, we will see a shape like this, where the thick area means a high concentration of latency measurements around that value, and a thin area means few measurements. We also identify the average of the series with the white circle, and the two dashed lines delimitate 50% of all measured samples. The different nodes depicted in the x-axis are parts of different computation paths. For instance, some of them are used for detect and track objects performing the scene perception using the LiDAR input, while others will be used to perform localization. Sometimes a node is used by more than one path. This occurs, for example, with the points downsampler in the right, which is used both for localization and also for asserting the road occupation using raw LiDAR points. Also, image-based perception, including object detection, tracking, and motion estimation based on the camera's input, will also appear. Frequently, once objects has been detected by either LiDAR or camera, they will eventually be fused to be handled by the same set of algorithms as we approach the end of the perception. Again, we invite you to check our paper where we overview the purpose of each node that we investigate. Autoware allows us to select different algorithms or implementations to be utilized by some nodes, increasing the system flexibility. We exploit this here by setting different vision detection neural networks. Two with SSD topologies, namely SSD 512 in the left and SSD 300 in the center, and also a darknet YOLO version 3 in the right. We do this to verify how changing these vision detection neural networks can also change the system metrics. Each time that we change the topology or implementation, we completely re-stimulate the nodes of Autoware using the same inputs. And that's why you see three charts here. From the charts, we can see that changing the vision detection from SSD 512 to the two other options can lead to a clear reduction in both average and tail latency. Also, the performance of other nodes in the system might be influenced by the chosen vision detection algorithm. For instance, verify the tail latency or worst-case latency of the road occupation node when running together with SSD 512 and compare to the smaller and more predictable latency that the same node presents when in the two other cases. The same can be seen for the localization task. In general, we can see a set of 6 or 7 nodes that have a high tail latency and are better candidates for improvement. This is useful since it narrows the search for nodes to optimize. Now we analyze the latency of the different computation paths, which are those that we labeled in 4 groups before identifying them with different colors. Recall that when we analyze the computation path, we are taking into account the processing time contributed by each node on that computation path, and also the time devoted to pass the messages between one node to the following. To help visualizing the findings, we place a 100 milliseconds mark in the 3 charts. Recall that each chart is Autoware with a different vision detection implementation, as I just explained in the previous slide. The 100 millisecond mark is generally defined as a target reaction time for autonomous vehicles in previous works. Hence, we would like to see all computation paths always finishing their processing within this deadline. Unfortunately, this is not the case, and it's clear that Autoware struggles to meet the deadlines. For example, when using the SSD 512, the sequence of nodes that utilize image-based inputs to perform the perception has an average latency above the specified threshold. For many other cases, the computation path meets the deadline in the average, but not always. This means that there are times where the system takes too long to react, which is also unacceptable. From our experimentation, only the computation path that infers localization is able to meet the deadline in all cases, where all other computation paths struggle to do so. Now let's take a look on the hardware usage and power dissipation during Autoware execution. First, we notice that the CPU power does not vary too much even when we change the vision detection algorithms, since the CPU is used by all nodes. In the GPU case, that is mainly used by these vision detection algorithms, however, the GPU usage drops considerably when changing the SSD topology. As we can see, this has a great impact on the overall GPU power dissipation that goes down by a factor of almost 2. In overall, the GPU dissipates more power than the CPU, although it is used by fewer nodes. This indicates a bottleneck in power consumption that can support the claims for using specific hardware to execute these GPU-based algorithms. In general, the timeshare usage of the hardware is low, below 40%, which means that most of the time the hardware is idle waiting for the upcoming input frames from the sensors. Here, I'll try to cover some microarchitecture characterization that we performed. We have selected nodes with either high average latency or high tail latency, or among the top ones in the CPU-GPU usage regard. In the left, we present the instruction mix for 6 nodes, separated by load, stars, branches, and other types of instructions. And in the table on the right, we present microarchitecture metrics measured during the execution of each of these nodes. For example, we found out a large amount of branch misprediction for the SSD 512 when running on the CPU part. This occurs on the final layers of detection, where the algorithm has to sort the bounding boxes of the detected objects by the quality of their assessment. YOLO, on its turn, does not face such problems with unpredictability. The Euclidean clustering algorithm that is used to identify surfaces and objects on the data input from LiDAR has a considerable amount of first-level cache misses. This indicates that the memory pattern can be further investigated in the search for improvements, especially because the loads and stars account for 50% of the instructions executed by this node. The entity matching algorithm used for localization also suffers from range mispredictions. This might be caused by the irregular axes along the tree data structure that holds the LiDAR points used by this node. The last two algorithms for tracking and for defining a grid of occupied positions in the environment, which is named cost map generator, does not have any clear microarchitecture drawbacks. The tracking has some first-level cache misses, which might help explaining the small IPC, but the cost map achieves more than 2 instructions per cycle in our Intel i7, performing quite well. This can be explained by the fewer memory operations of these nodes compared to its counterparts. Finally, we present a deeper comparison between two vision detection nodes, SSD 512 and YOLO version 3. Also, note that we execute the vision detection in isolation and together with all nodes to compare what is the impact of sharing the resources might have on the latency. We first underscore that the two nodes have a substantial difference in usage of the hardware. SSD has a more or less equal separation between GPU and CPU time, while YOLO mainly runs on the GPU. When the nodes go from isolated execution to run in combination with other nodes, we perceive a 12% increase in the mean time latency for SSD and a 6% for YOLO. Also, the standard deviation increases by more than 4 times in both cases. During our characterization, we had found out a few important findings. We saw that different computation paths do not meet the 100 milliseconds time deadline. We saw opportunities for improving in LiDAR-based nodes and not only image-based nodes that are more trendy currently. Also, we saw that changing the vision detection algorithm imposed great changes in the latency and power consumption, especially for GPUs. And also, we showed that measuring the system with the complete setup with all nodes is mandatory for properly assessing the tail latency. If you enjoyed this presentation, I would like to invite you to read our complete paper where we present all the characterization in more detail. Once again, I would like to thank you for attending this talk. Goodbye.